Here we are once again. It's your friendly heavy physics teacher, and we have a Regents Physics lesson, and I may double this up for my college physics guys. So we'll see. But for the Regents Physics class, this is your lesson on refraction of light. It's going to be an introduction to how we use Snell's law in defining the refraction of light, okay? So this is Unit 12, Lesson 3.2. This is the second half of the lesson that deals with the reflection of light and introduces the refraction of light, and specifically the properties of transparent materials that create the refractive effects that we can relatively easily measure. Okay? So, in the last unit, we talked about refraction in general terms, and we said refraction, we defined it as the change in speed of a wave as it crosses a boundary between mediums. This change in speed, if the path of the wave makes an angle to the boundary between the mediums, then the path of the wave is also going to bend and change. Because when the speed changes for the wavelength must change. The thing that remains the same for the wave crossing the boundary between the mediums is the frequency. And that is key to remembering, or a key thing you need to remember as we talk about the refraction of light. The way we know that the frequency is not changing for light, if you were to shine a red light, say like a laser pointer, from the air into a tank of water, say a fish tank, you would see the red light, and it would be the same red light in the water as you see in the air. Okay? That's how we know the frequency hasn't changed. And yet, if you measure the wavelength of the red light in the water and you measure the wavelength of the red light in the air, they're going to be two different numbers. It is that difference in the wavelengths which lets us know how much light has been slowed down by entering a transparent medium. Now, this phenomenon can be seen. Okay, time to get spooky on your butts. I know this is kind of weird, and I know it's really, really sudden, but what I've had to do is jury rig a system by which I'm going to demonstrate some refraction for you. Okay, so bear with me. What I've got here is this clear plastic container, and I put some water in it, and you'll notice that I put a little bit of milk in the water, and notice that when I shine my light in the water, it's creating this huge dispersive effect. Okay, the milk particles in the water are scattering the light that's going through it. And you can't really see the beam of light that I can see going through the water because of how that's scattering. So what I did was I took a sheet of cardboard, all right, and as you can see, I put a hole in it, and that limits the light that's coming out. And notice that I can now create a beam of light. Now let me center this. Okay, you see the beam of light going through? Now, I can make that even more of a column. Watch this. Take a straw, all right, put it through the hole I made, and put the straw up to the light. Make sure I center it on the light. Oh, I've got my own lightsaber. Oh! And notice that that creates an even better column of light. Now, when it goes into the water there, all right, and we're going pretty much at a perpendicular line, notice that you can't really see any refraction. But if I tilt this, and if I tilt it at a very extreme angle, notice that the angle the light is making in the water is different from the angle the straw is making with the side of the glass. All right, another way of showing that, okay? See how there is a bend? You can quite literally see the bend as the light is coming out of the straw and entering the water. Okay? Now the reason you know that that's going like that is if I put the straw in the water, notice it comes straight out. Okay? But if I pull it out again, notice that the path of the light is bent as it enters the water. And the same thing over here, it bends the other way because as I make this angle with the side, all right, you see how it's getting bent in there? All right. And so that's refraction. That's the refraction of light that's happening as the speed of light changes from the speed that's coming out of the flashlight here and going into the water. Okay. Now, as I said, the speed change can be measured because it's a proportional change in the wavelength of the light. So if you measure the wavelength in the water, you measure the wavelength in the air, and you make the comparison, that ratio is going to be the same ratio as the difference between the speed of light in air and the speed of light in the water. Well, it is this ratio and that angle change that we can measure. And by doing that, we can determine optical properties for a medium. One of those optical properties is known as the absolute index of refraction. Okay, absolute index of refraction is the ratio of the speed of light in a vacuum to the speed of the light in the transparent medium. Okay, and the absolute index of refraction is always for a particular wavelength or a particular frequency of light passing through the transparent medium. Each wavelength, each frequency has a slightly different absolute index of refraction, and that will become important to us when we talk about the difference between white light going through a medium and monochromatic light. Mono meaning single, chromatic meaning color. So monochromatic light is single color light. All right. And so this is true for a single color of light moving through a transparent medium. The absolute index of refraction, we use letter N to represent that, is equal to the speed of light in a vacuum, C, celeritas, divided by the speed of light in the medium. Okay? All right. Now, if you get your reference tables out, and on the same page that has the electromagnetic spectrum, on the bottom of the page is a table of absolute indices of refraction. And you'll notice at the top of the table it says for F equals 5.09 times 10 to the 14 hertz. Well, if you translate that into a wavelength, that means for a wavelength of 5.89 times 10 to the minus 7 meters, then you get these following indices of refraction for that color of light. The color of light happens to be in the range of just in between yellow-green, all right, right in the middle of the visible spectrum for us, okay? So if we look at water, the absolute index of water, H2O, is 1.33 for that wavelength, which if you use the equation, N equals C over V, and solve it for Vm, in this case, the M would be water, you'd get a speed of 226 million meters per second, 2.26 times 10 to the 8 meters per second. if we used vegetable oil, and I just said N oil here, but if it's vegetable oil, the absolute index of refraction for this wavelength is 1.47 times 1.47. So if I put that into the equation and solve for Vm, the velocity of light in oil is 204 million meters per second. You can do the same thing for crown glass. Notice that on the reference table, there's two entries for glass. One is crown glass, one is flint glass. Crown glass, the reason it's called crown glass was at the time of ancient glassmaking, it was a more expensive process that produced glass that is what we normally see in our windows. Didn't have bubbles, didn't have ripples, didn't have any sort of flaws in it. Flint glass is a very cheap and quick, easy way to make glass, all right? And it's actually slows down light more. Look at the reference table and you see that flint glass, instead of being 1.52, flint glass is 1.66, okay? So crown glass slows down light almost 1.5 times, okay? Diamond. Diamond is a transparent material that has one of the slowest speeds of light through it, okay? Diamond, the speed of light in a vacuum is 2.42 times. In other words, 242% faster in a vacuum than it is in the, or I should say 142% faster than it is in the diamond. Okay, so if you use that equation, the absolute index of refraction of diamond is 2.42. So the speed of light in a diamond is only 121 million meters per second. Yeah, million meters per second. Okay? Now, a Swedish scientist looked at these ratios, and they were using wavelengths, but it's the same ratio for wavelength as it is for speed. And he very accurately measured the path that light moves through one medium into another, and measured their angles of incidence and angles of refraction, and he came up with a relationship for it. And so we honor Willebrord Snell. Yeah, that was his name, Willebrord. Willebrord Snell, S-N-E-L-L, with Snell's law, okay? And in a lot of words, it's this equation down here, all right? The ratio of the sine of the angle of incidence, and we're going to designate angle of incidence as theta 1. The ratio of the sine of angle of incidence to the sine of angle of refraction, theta 2 will be the angle of refraction, is equal to the index of refraction in the refracting medium, N2, divided by the index of refraction in the incident medium, N1, okay? Or, as it's written on the reference table, N1 sine theta 1 equals N2 sine theta 2. And this is Snell's law. This is how you can use it to either determine a likely angle of refraction in another transparent medium as the light moves from one to another, or if you can measure those angles, you might be able to determine the optical properties of an unknown transparent medium. Here are some examples of how to use it. Okay, think about my demo that I did a little earlier, okay? I had the light ray coming out of the straw in the air over the top, not on the side. This is over the top. The light ray was coming out of the straw in the air, entering the water, and you saw it make a smaller angle, an angle that was more vertical in the water than it was up in the air, okay? And so if I were to measure the angle that I had the straw at with the boundary, and then determine the angle of incidence, let's say that my angle of incidence was 30 degrees, okay? So using Snell's law, n sine theta 1, n1 sine theta 1 equals n2 sine theta 2, make my substitution, do my algebra, in the water, the angle is 22 degrees. Now, yeah, I know my diagram over there isn't really to scale, but it's to emphasize the fact that, oh, I'm going from a index of refraction that is low to an index of refraction that is high, meaning that this permittivity, it's the reverse of permittivity, okay? Your index of refraction, if you compare the index of refraction of one material to the other, it's the opposite of their permittivities. Light moves faster in air than it does in water. The higher the index of refraction, the slower the speed. The higher the index of refraction, the slower the speed. Therefore, the higher the index of refraction, the lower the permittivity. So we're going from a high permittivity, air, low index of refraction, into a low permittivity, higher index of refraction, water. Notice that my refracted angle is larger or is smaller than my incident angle. My refracted angle is smaller than my incident angle. Okay? An example of the reverse of that, only this time we don't know what the second medium is. A zircon is a type of mineral that is often used for costume jewelry. All right. It's, you can almost think of it as a form of quartz. It's not really a form of quartz, it's its own mineral, but it's, you can think of it as quartz. It's very clear. Okay. And zircon has an index of refraction of 1.92, very high index of refraction. And so we're saying we're going from zircon into some other transparent medium. All right. It could be just as clear, seemingly as clear as the zircon. And so the light can easily pass from one to the other. All right. So let's say that in the zircon, the angle it makes with the normal line, the angle of incidence, is 25 degrees. And we measure, let's say this is a laser, a beam of laser light. And we're able to measure the angle over here in the unknown refracting medium. And that angle is 32.26 degrees. If we make our substitutions, then the algebra leads us to an index of refraction in the refracting medium of 1.52. All right? So look it up. What is that? Well, if you remember from a few minutes ago, that would be the same index of refraction as crown glass. So probably this unknown medium over here would be crown glass. And you'd see some difference between the zircon and the glass, but maybe not a lot, okay? But the fact that the path of the light bent lets us know that we've got a new medium, all right? Okay, so we have got a technique for measuring how much refraction transparent mediums will do to light as it goes from one medium to another medium. Interestingly enough, there are certain mediums that have the same transparent properties. If you look on that table, you'll notice that glycerol, a clear, thick liquid, and vegetable oil, normally a yellow color, think of olive oil or corn oil, okay? If you were to put the two on each other, the oil would float on top of the glycerol. But if you were to pass a laser beam between the two, there would be no change because the optical properties of the oil are the same as the optical properties for the glycerol. And so there would be no change in speed, there would be no bending, and the light would go through, and all you'd see is that path of light going from the yellowish substance into the clear substance. All right? So, refraction of light is the same as any other refraction. We just now have a particular way of measuring it that compares speed of light in a vacuum to the speed of light in the medium, gives us the index of refraction. We can then use that index of refraction and the angles of incidence and angles of refraction to make measurements about the path that light will take as it moves from one medium to another. Okay? Thank you very much and have a great day. I will see you soon.